Hello. We're going to be talking about Lewis structures. This is probably the most useful thing you're going to learn because Lewis structures is the gift that keeps on giving. You're going to need them for many other topics in chemistry. Okay? You're going to study three-dimensional structure of molecules. Write a Lewis structure. You're going to study thermochemistry. Write a Lewis structure. You're going to compare the strengths of different acids. Write a Lewis structure. So if you get it right now, it will help you a lot later on. Lewis was a genius, in my opinion, and I don't say that lightly. To me, a genius is someone who takes something very complicated and makes it easy enough that I can understand it. Do I think that Einstein was a genius? No. He was extremely smart. He was a great mathematician, physicist, whatever. But when you read what he wrote, I don't understand most of it. So to me, that's not a genius. Lewis got a very complicated thing and made it so easy, like the commercial says, a caveman could do it. Okay? That's why I call him a genius. The problem when I was an undergraduate is, well, that was a long time ago, that was a different country, and my chemistry instructor said, there are no rules, memorize as many of these Lewis structures as you can. I did my best, and the two Lewis structures that were in the exam were not any of the ones I had memorized. That's not fair. Well, fast forward, I'm now in Washington, D.C. I'm taking advance in organic chemistry. We get to Lewis structures. I'm all excited. And the instructor says, memorize as many as you can. There are no rules. You've got to be kidding. Well, a few years ago, I was teaching at a technical college, and we was looking for ways to improve the grades. So the department head got together all of the chemistry instructors, and said, what is the most common thing that the students have problems with? And we all answered, Lewis structures. Yeah, if we could get them to understand Lewis structures, it would make such a difference in their grades, because we use them all the time. Okay. Now, by that time, some of the textbooks had little hints. If you do this, it may help. If you do that, we found hints on the internet. She said, I tell you what, send me an email with all of the so-called hints, and we'll meet again in a week. So when we met together again, she had printed out all of the hints that we had collected, and we went through them one by one. Well, this is a good idea. This helps. No, this is just an old wives' tale. This, I'm not sure. If we do something else before, then it will be helpful. So we went through all of the things, we played with it, and we came up with a set of rules that if you follow them, it answers most of the molecules. And she said that's good enough. Okay? Now make sure when you're giving a molecule an exam, it's one of the molecules that you can solve with these directions. And we dropped it there. I wasn't satisfied. So eventually I left that place and I kept going over the rules, making changes, trying this, trying that. It took me a year. But I finally have a set of rules that if you follow them exactly the way I describe it, in the same order, that's critical that you follow the same order, you always get the right answer. Isn't that good? I'm not saying there isn't any exception, but I've been using those rules for 8 years now. I still haven't found any molecule that if you follow those rules, you don't get the right Lewis structure. So that says something. Actually, someone told me, you ought to publish that in the Journal of Chemical Education. Well, the problem is it started as a cooperative project, and I don't think that's ethical. Never mind. I'm beyond worrying about things like that. But I'd be glad to share this with you. To begin with, what is a Lewis symbol? Lewis said, the problem is when we represent an atom, we put all of the electrons, and that's what makes things so complicated. But the only electrons that actually participate are the valence electrons. So why do we have to draw the others? Why don't we just represent only the valence electrons, and we're going to represent them with a dot? Now, he said an atom is going to be, you're going to represent with a symbol. It has four sides, right? You have the top, the bottom, the right, and the left. If you put two dots in each side, you have the octet. One thing that most textbooks don't tell you is never put two dots on the same side when one side is empty. Even though that's one of the rules that Lewis said. Look at magnesium, for instance. If you put the two dots in here, first, this is not what Lewis said. And let's face it, it was his idea, so he can set the rules. But it doesn't make any sense because the two electrons are going to repel each other. They don't want to be on the same side. So you can represent it like this, opposite sides, or it's acceptable, according to Lewis, if they're side by side, as long as they're on separate sides. How do I do it to make sure I don't make a mistake? Let's think, for instance, chlorine has 7, so I start 1, 2, 3, 4, 5, 6, 7. By putting 1 on each one and then continuing, I never leave a side empty. Okay? Like I said, it is Lewis's rule, and it helps you see much better. This is one of those cases where doing the right thing helps you so much that it doesn't make any sense not to do it. Lewis symbols are very useful to show how ions are formed. You can see sodium has only one dot. When it loses that electron, it becomes a sodium ion. Chlorine has 7 dots. It's very easy to see that you just want to add another dot in there, and then you have the chlorine ion. One thing that drives me crazy is that Lewis said all of the ions had to be placed in brackets, square brackets, and put the charges outside. Not all textbooks do that. Some put brackets in all of them, that's fine. Some put the brackets on only the positive ions. Some put the brackets only on the negative ions. Some don't put brackets at all. Once again, it's Lewis's idea, so it's Lewis's rules. But most important, it helps you. The idea of the brackets is one, it lets you see you're dealing with an ion. And when you talk about polyatomic ions, you don't know where the charge is. You wouldn't worry about where the charge is. The whole polyatomic ion has that charge. So by putting the charges outside of the bracket, we indicate that we're not telling the charges on this atom or that atom. We're not there yet. Once again, doing it the way Lewis said makes your life easier. Lewis symbols are very useful when you talk about covalent bonds. Here I have two chlorines. You can see the electrons are different color because that way you can see that the shared electrons, one comes from the chlorine on the right and one comes from the chlorine on the left. But when you write the Lewis structure, please do not write two dots for a bond, for the shared electrons. Use a line, okay? The non-bonding electrons remain as dots, but in this drawing here, it's very difficult to say who are the bonding electrons and who are the lone pairs. You can see it, but it's not as obvious as when you have a line versus dots. And when you get a big molecule, believe me, it gets very, very, very difficult. But anybody can tell the difference between lines and dots. So once again, doing it the way Lewis suggested makes your life easier. We're going to define lone pairs as the electrons not used in bonding. Yes, it sounds like an oxymoron. I agree. How can it be a lone pair? Either you're alone or you're in a pair. Well, that's what Lewis called them, okay? They're lone because they're not forming a bond, but they come in pairs. Always electrons like to be in pairs. A single bond is a single shared pair of electrons, and we represent it with a line, like we did in there. Okay? So you have some examples of Lewis structures. Ammonia has 3 single bonds, 1 lone pair. Water has 2 single bonds, 2 lone pairs. Hydrogen fluoride, 1 single bond, 1, 2, 3 lone pairs. Again, you see how easy it is to differentiate the single bonds from the lone pairs, because we follow Lewis' rules. Now, double bond, you have to be careful because students sometimes make mistakes here. A double bond is when you share 2 pairs of electrons between 1 pair of atoms. So you have carbon double bond oxygen. Here you have carbon double bond carbon. But I have the students tell me, oh, here there is a double bond between carbon and hydrogen. 1, 2, that's a double bond. No, because those are 2 different bonds. This carbon is bond to 1 hydrogen to a different hydrogen. But what I call double bond is the same carbon. It's 2 bonds between the same 2 atoms. You see the difference? These atoms are different, these are the same always. So a very important rule that you're not going to find in books is that 2 single bonds are not the same thing than a double bond. And this is very important because the properties of single bonds and double bonds are very different. If you move on to take organic chemistry, this is going to become a crucial part, understanding molecules, okay? Same thing with triple bonds. A triple bond, that means 3 electron pairs between the same pair of atoms, okay? 1 carbon, 1 nitrogen, triple bond. We are representing them with 3 lines. Carbon, oxygen, triple bond. But remember when we saw ammonia? We have 3 single bonds, but the hydrogens are different. So 3 single bonds are not 1 triple bond. And once again, the properties of the triple bond and the single bonds are different enough that this is very, very important. So let's try to write Lewis structures. I told you I had a step-by-step list of what to do. I'm going to explain it to you. If you want the written list, you need to make an appointment through Weiss and for Turing, and I will share that list with you. Otherwise, you can just listen to me explain it. So, silicon tetrahydride. The bonds are formed with valence electrons, so it makes sense we need to know how many valence electrons, right? Because we need to use exactly the number that we have. We cannot use more, we cannot use less. So you look at the periodic table, silicon has 4 valence electrons. Hydrogen has 1 valence electron, but we have 4 hydrogens, so we have 4 valence electrons there. Altogether, I have 4 valence electrons. The next problem is in which order we put the atoms. And the rule is we are going to put in the center the atom that can form the most bonds. Okay? So how many bonds can silicon form? 4. Why? Because it has 4 electrons, it wants to have 8. So by sharing in 4 bonds, it fulfills the octet rule. Hydrogen can only have 2 electrons, so it can only form 1 bond because that fills the outermost shell. So who can form most bonds? Silicon. So we put silicon in the center, surrounded with hydrogens. And now we're going to put a single bond. Always begin with a single bond. No matter who the atoms are, no matter what you're guessing, just follow the rules. Form a single bond. Now we have 4 single bonds. Each one has 2 electrons, so I use 8 electrons. There's none left. So I'm finished. That is the Lewis structure for silicon tetrahydride. Now you can ask, what happens if there's leftover electrons? Let's look at an example for that. Okay, so we begin. Carbon has 4 valence electrons. Hydrogen, 1 valence electron. Oxygen has 6 valence electrons, but we have 2 oxygens. Notice that. So we have 12 valence electrons. And now the negative charge in there was going to be 1 more electron. So altogether, I have 5, 17, 18. 18 valence electrons to play with. Once again, who goes in the center? The one that can form the most bonds. Carbon, which it can form 4 bonds. Just like silicon, it has 4 electrons, so it can form 4 bonds. 4 plus 4 equals 8. We said that hydrogen can only form 1 bond. Oxygen, well, each oxygen can form 2 bonds, because you have 6 electrons. So if you form 2 bonds, you have 8 electrons. So who goes in the center? Carbon. So we're going to put carbon, hydrogen, oxygen, and oxygen. Then what do we say? Next, we're going to form a single bond. So I have used 2, 4, 6 electrons. So I have 12 electrons left. Then you start putting the leftover electrons on the outside atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I use them, so I'm finished with that. Are all the atoms happy? Hydrogen is happy because it has 2 electrons and that's all it can hold. Oxygen has 6 and 2 from the bond, 8. Oxygen is happy. Same thing with our oxygen. How about carbon? 2, 4, 6. No, carbon wants to have 8. When that happens, and usually it's the center atom, when it does not fulfill the octet rule, it borrows one of these lone pairs to form a double bond. So let me draw it again so you can see it good. This oxygen had 6, and now we have only 4 left in there. Now every atom is happy. We already look at this one. Carbon has 2, 4, 6, 8. Oxygen 2, 4, 6, 8. Everybody's happy. We're done. The only question you could ask is, why borrow the lone pairs from this oxygen? Because if you borrow from the other oxygen, you end up with the same molecule. Really, you have a double bond here, 2, 3, 4, and then this is going to remain like that. These 2 molecules are the same molecule, okay? It's a carbon, single bond hydrogen, single bond oxygen, double bond oxygen. It's the same molecule. But the key is the leftover electrons, we put them over the outside atoms. And if the inside atom does not fulfill the octet, we borrow some of those to form multiple bonds. NO plus. Okay, nitrogen has 5 valence electrons, and by now you know 3 bonds, because 5 plus 3 equals 8. Oxygen has 6 bonding electrons, so it can form 2 bonds. Not that it really matters, because when you have 2, they're going to be side by side anyhow, but sometimes it's good to get in the habit of doing things. Now, a positive charge, that means that you lost an electron. Okay? So you don't have 11 valence electrons, you have 11 minus 1, 10 valence electrons. So we put nitrogen, oxygen, like I say, it doesn't matter. We use 2 electrons, we have 8 electrons. Now, what most students ask me is, okay, we don't have enough electrons to cover everybody. So, should we start on the nitrogen? Should we start on the oxygen? Actually, it doesn't matter. And if you don't mind, I'm going to prove it to you, because I said it doesn't matter, and many students still get obsessed with that. So let's start with oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Or with nitrogen. 1, 2, 4, 5, 6, 7, 8. In this case, oxygen is happy, nitrogen is not. It has only 2, 4. So it's going to borrow 2, and it's going to form a triple bond. In this other case, nitrogen is fine, oxygen is not, so it's going to borrow. Since it has 4 electrons, it needs to borrow 2 pairs. So you're going to have nitrogen, triple bond oxygen. You see, I come up with the same answer. So there's no rule in here. You can begin with any atom you want, and you still get the same result. Once I use those 8 electrons, I have 0, everybody's happy, so that is my Lewis structure. Okay? It's not that difficult. OF2. Okay? Oxygen, 6 valence electrons, forms 2 bonds. Fluorine, look in the periodic table, has 7 valence electrons, but we have 2 of them, so there's actually 14 valence electrons there. Because it has 7, it can only form 1 bond. Altogether, we have 14 plus 6, 20 valence electrons. Who goes in the center? Oxygen. Why? Because it forms more bonds. So you're going to have oxygen, fluorine, fluorine to form a single bond. So I use 4 electrons. That leaves 16 valence electrons. We begin 1, 2, 3, 4, 6, 7, 2, 6, 8, 10, 12. So I've used 12 electrons. There's still 4 valence electrons left. Whenever you have leftovers, what do we say? We are going to put them on the central atom. 1, 2, 3, 4. These are the 4 leftovers. We have to put them someplace. We already filled the outside atoms, so we start putting them on the central atom. And now we look to see if everybody's happy. Fluorine has 2, 4, 6, 8. Okay. Oxygen, 2, 4, 6, 8. Fine. There are fluorine, 2, 4, 6. They're all happy. You're done. Like I said, this is not difficult, but if you get my reading step by step, especially because it will emphasize in which order you do things and all of that, you can get a worksheet where you're going to write Lewis structures, you can get the rules, and like I said, just follow them side by side, and you learn it practicing. Practice makes perfect, but only good practice makes perfect. That's why you need the rules. And that's what I'd be glad to share with any of my students. Now, there are exceptions to the octet rule. Okay? There's molecules that have an odd number of electrons. Octet means 8. What if you have 7 electrons? Oh boy, there's an odd number of electrons. We call that a free radical, and we're going to look at them in a moment. Some molecules, we call them incomplete octets because they don't have 8. That doesn't necessarily mean anything wrong. We're going to look at some examples where you don't have 8 electrons, but they're fine because they're very, very small atoms. And some, if they're real big, you have expanded octets. And I want to say a couple of words about each one of them. This is an example of a free radical. Notice 2, 4, 6, 8, 10, 11. Oh, that's an odd number. You can tell you don't have a lone pair, and there you have only 1 nitrogen, 1 electron in the nitrogen. This is very dangerous biologically because molecules and atoms don't like a lone electron. They like to be in pairs. So this molecule is going to steal an electron from another molecule, which will make that molecule a free radical. And that's like a chain reaction. And it causes lots and lots and lots of problems in your body, can lead to aging, cancer. Fortunately, there's a number of vitamins that help with that. There is antioxidants. Why is it good to eat broccoli? To prevent cancer. And it's true, okay? I had stage 4 cancer, had surgery. The doctor gave me a year to live 10 years ago. You know what I did? I had a lot of people praying for me, and I also started eating broccoli. But I hate broccoli. I started asking my friends, and they started bringing me different recipes. You know what? I have 3 different recipes for broccoli casserole. I love all 3 of them. They're slightly different. And I love broccoli salad. And I love, all of a sudden I found out different broccoli recipes that I love. What other food is good for you that has antioxidants? Blueberries. Oh, come on. Who doesn't like blueberries? basically, you're talking about compounds that neutralize free radicals. Free radicals are going to appear in your cells as part of the biochemical reactions, but if you eat the right food, you neutralize the free radicals. Okay? This is my little anti-cancer speech. In complete octets, we talk about halogen. Beryllium can only form 2 bonds. Boron can only form 3. If you look in the periodic table, that's what brings it the easiest to full first level cell. So just learn those 2, memorize it. Those are, well, and add hydrogen. Okay? So just need to remember beryllium, boron, hydrogen, they form incomplete octets. They have a full outermost shell, but it's not 8 electrons, it's 2, because there is more. Now, when you get to the 3rd period and higher, you go to the periodic table, you get into the 3rd row, then sometimes you have more than 8 electrons. Okay? Why? You're going to have empty d orbitals. Didn't I tell you I was going to blend the d orbitals for lots of things? So look at this particular phosphorus pentachloride, 2, 4, 6, 8, 10 valence electrons. The sulfur, 2, 4, 6, 8, 10, 12. And sometimes, excuse me, when you're doing the Lewis structure, you may end up that you still have electrons left over. We said you put them in the center, but now the center has more than 8. That's okay, as long as the central atom is in the 3rd period or below. No, iodine is in the 5th period, so it's okay. Xenon is in the 5th period too. So it's okay if they have more than 8 electrons. Okay? Now you don't try to purposely force more than 8 electrons. You're going to follow the rules. And then you find that if you follow the rules, there's only one solution, there's only one answer, and your central atom has more than 8 electrons, and then you say, okay, wait a moment. In the central atom is in periods 1 or 2, I made a mistake. Let me go back again. But if it's in periods 3 or below, it's okay. The atom is big enough to handle it. Don't force it. Follow the regular rules, but if the central atom has more than 8 electrons and is big enough, it's okay. Now, I understand this is complicated. You probably would like to have the hand that I told you, describing you step by step, and especially in which order you do things. So if you go to my video description and make an appointment in my Wisant account, I will meet with you and you will get a copy of the step-by-step guide on how to do it, and you will get worksheets to practice. It's really not that difficult. It just takes practice. Practice makes perfect. The more you practice, the better you'll be. And remember, you're going to need Lewis structures over and over and over later on in chemistry. So you want to get them right now.